Yeah, thanks very much for inviting me to speak at the conference, at the workshop. So, yes, okay. So this talk actually is, I just would like to speak about how part of the endoscopic classification of Arthur could be formulated in the this context of beyond endoscopy. And so in this talk, everything will be done on the spectral side. Okay. So let's begin with an overview. In the first part, we just give a review of the endoscopic classification. Okay. So and then, as I said, okay, in the second part, so I would like to try to reformulate it in the context beyond endoscopy, following Arthur's paper. Problems beyond endoscopy. Okay. In the third part, so this is about constructing certain limiting forms of the stable trace formula. So this is what Langlands proposed, namely that for a representation, finite dimensional representation of the R group. So what Langlands proposed is one try to use modified test function to construct some limiting form of the stable trace formula and hopefully get some form of this beyond endoscopic decomposition also in these limiting form of the stable trace formula. So this is a very difficult problem, but by combining known results on L function of length Shaidi type, so we will see that for the first two fundamental representation of a dual group, we can see what are the limiting forms. Okay. And then I will end with concluding remarks. And so let's just give a review of the endoscopic classification. Okay. So firstly, okay, so for the generality, G will be any connected reductive group of a number field. I will assume is a quasi-split. Eventually, we will take it to be the split odd orthogonal group. So in any case, for simplicity, I assume that this AG, so namely the maximal F-split component of center of G is trivial. Okay. So as usual, we have the L2 space of automorphic functions, and we are interested in the discrete automorphic spectrum. Pi ranges over the irreducible unitary representation of the arithmetic points of G. Okay, M pi is a multiplicity. So the general conjecture of Arthur is to give a understanding of the decomposition of this L2 discrete spectrum. And the general conjecture framework is that is parameterized by these parameters. Okay, we have already seen these a number of times. So LF is a so-called automorphic Galois group or the Langlands group. So that I will say, come back to this a moment later. Okay, cross this alpha SL2 to the L group of G. So those psi that would contribute to the discrete automorphic spectrum are square integrable parameters. So namely, do not factor through L group of M for any proper Levy subgroup M of G. So we denote by psi of G the set of global alpha parameters, while the subset of square integral parameter will be denoted psi 2 of G. Okay. So LF, as I said, the automorphic Galois group over F. So it is, for our purpose, we don't really need this. In fact, the existence of this is highly conjectural. But in any case, in fact, Langlands in recent times, he himself doubted the existence of this. But in any case, so conjecture to be a locally compact topological group. So it's in some way, it's a soup-up form of the global Weil group, the surjectional global Weil group with compact connected kernel. And the main point is that this have a Tanakian type characterization. So namely for any integer n, so an n-dimensional irreducible unitary representation of LF, okay, like this, would correspond to a unitary cuspidal automorphic representation, pi phi of GLN. So of course, there's some kind of local global compatibility one would need. So namely that for each place V of a number field F, okay, so there ought to be a injection of this local Langlands group or Weil-Deligne group at the place V to the LF. So that ought to be compatible with the local Langlands correspondence for G of n. So namely that just in the usual sense that, okay, right, okay, yeah, in that case. So if you have a phi, and if it corresponds to a cuspidal automorphic representation, pi phi, then if you restrict the parameter phi to the local Bayesian group, yeah. Okay, yeah. Yeah, okay. Right, so this, okay. Then this would correspond to the local component pi phi v under the local length correspondence, okay, for G of n. Okay, yeah. So in more detail, so given a global alpha parameter, so we would like to construct a global packet. So this consists of irreducible unity representations of the adelic points of G, and is given by restricted tensor product of the local alpha packets. Okay? And in the particular case when the parameter is square integrable, so one would want a formula, multiplicity formula for a representation and packet to occur in this discrete automorphic spectrum. Okay? Yeah. So, and in addition, I want to show that conversely, any pi that is in the discrete automorphic spectrum belongs to such a global packet for a unique square integrable parameter. Of course, once we know how to describe the discrete automorphic spectrum for G and also for the Levy subgroup, then Langlands theory of Eisenstein series give us the complete spectral description. Oh, yeah, right. So now we will actually focus only on the parameters that are generic. So namely that those parameters that are actually trivial on the SL2C of alpha. So in other words, a generic parameter is simply such a map, okay, from LF to LG, okay? And we denote the set of generic parameters as phi of G. So then, just as before, so given such a parameter, we can look at a localization at the local Bayesian group at the place B. And so this is a local L parameter for G at the place B. And we would also like to have a local length correspondence for G over FV. So such a parameter would correspond to a local L packet. All right. So, okay, so this is the general framework of Arthur's conjecture. So it has to be added the following point. So namely an extension of the generalized Ramanujan conjecture. Okay. So namely that if pi is in the discrete automorphic spectrum, then it's Ramanujan type, namely temper at every place of V, if and only if pi is classified by such a parameter, namely square integrable and generic. Okay. So these will play an important role. So we will call these parameters, so denote phi 2 of G, namely those that are generic and square integrable and referred to as cuspidal parameters. More accurately, a better name perhaps is both cuspidal and temper, namely that the automorphic representation in the L2 spectrum that are both cuspidal and temper, okay? But for simplicity, we just refer to these as cuspidal parameters, right? Yeah. So in the following, we often fix a finite set places containing all the Archimedean places. So, and let's say that we have a pi in a global alpha packet for a certain generic parameter. Let's say pi is unramified outside S. Then, as usual, we have the Langlands L function, okay, defined respect to a finite dimensional representation of the I should use the L group, but eventually we're going to have the split case, okay, so it should be L group G, okay. For us, okay, so because this would depend only on phi, on the parameter phi that classifying pi. So in what follow, we denote this Langlands L function as L S phi R. So now, as I said, we now take G to be a split special odd orthogonal group over F. Okay, so like this. So it's split. So we just work with a dual group. Dual group is the symplectic group. In this case, for classical groups, okay, orthogonal and symplectic groups. So in particular for odd orthogonal groups, so the general conjectures of Arthur, okay, were established in his book with appropriate understanding. So namely that we certainly don't have this automorphic Galois group. So therefore one has to make a certain substitute of that. But this could be done in the context of classical groups. So this, for example, is the main, how this is done is described, for example, in chapter 1 of Arthur's book. The generalized Ramanujan conjecture is, of course, something we don't have, but so therefore one has to work around that, but this is also described in there. Okay. Yeah. So now a parameter for G that is cuspidal could be described quite concretely. Okay, so namely that, okay, so as we have seen a number of times already in this program, so all right, so in our case with a G dual, it's just symplectic group. And then you just view everything inside the linear group. All right, then so if we do have such a LF, then when we push to the general linear group, then it would factors as a decomposition like this. Okay, so phi1 up to phi k. So here, each phi is irreducible, and secondly, because its image is in the symplectic group, so therefore each of these phi is of symplectic type. Now, since we don't have the Lang-Length group, so what we simply interpret this as saying that, okay, each phi is a unitary cuspidal automorphic representation on GL of 2mi, okay? And then to say that phi is symplectic type is a condition that could be described in terms of the exterior square L function, which is of Lang-Length Chahidi type, okay? So you simply interpret this phi as a automorphic representation of the general linear group, okay? And phi and phi j are non-equivalent for I not equal to j. And then, of course, this condition, okay. So these 2mi is a partition of 2n. So if k equal to 1, namely if there's only one such thing, then we call the parameter as simple. Okay, so denote as phi simp G. So the question is, how is this endoscopic classification reflected in the stable trace formula? So more sophisticated form is, so can we formulate this portion of the endoscopic classification in the context of beyond endoscopy? Okay. So we work with the stable trace formula. So as usual, the Hacker space of test functions. To begin with, we have the invariant trace formula. Okay. So as usual in the geometric side, so we have these, in some sense, most important terms coming from the L2 discrete spectrum, so multiplicity and character. And on the geometric side, we have the these global coefficients associated to conjugacy class of GF and then orbital integrals. So I will not describe the more complicated terms because in any case, they're not going to show up in this talk. So for our purpose, we need to work with the stable version, so which looks quite similar to the previous, to the invariant version. Okay, so except that, say for example, in the spectral expansion, so here, so the dominant terms begin with those. So now we replace, say for example, on the spectral expansion, we work with packets. Okay, and then so the dominant terms come from the packets parameterized by the square integrable parameters, square integral alpha parameters. Then we have the stable character associated to the packet corresponding to psi, and then there's a stable multiplicity. Okay, so the stable multiplicity in general is a rational number. Okay, yeah, and then similarly on the geometric expansion. So here then the so here the sum is say over the stable conjugacy class, and then there's a stable version of these global coefficients and also stable orbital integral. So the distribution SG is stable, meaning that it depends only on the stable orbital integral of the test function f. So, however, for our purpose, even this sum is still too big, namely that we would like to only consider the sum over those cuspidal parameters, okay? Namely those that are generic and square integrable. Okay. Before that, okay, it has to be added this result. So this is one of the main results in Arthur's book, stable multiplicity formula. So for phi, that is a cuspidal parameter, okay, like that. Then there's the formula for the stable multiplicity is this one, okay? And the general multiplicity formula is a direct consequence of the stable multiplicity formula and the character formula for packet. Okay, so also note that in the generic case, the stable multiplicity depends only on the partition. In fact, it depends only on K. Okay, so this is not true for parameter that is not generic. Okay, so if the parameter is not generic, the stable multiplicity is more complicated. So it would depend on certain symplectic root number of the parameter, but in this case, it's quite simple. Okay, so now, as I say, so we want to consider only a subsum of this. Okay, so namely that we consider only this sum. Okay, so here you sum on the spectral side. We work only on the spectral side, so you form this sum, but the sum is only over the cuspidal parameters. So we call it the cuspidal component of the stable trace formula. So of course it's certainly stable because you just sum over a linear combination of these stable characters. Okay, so we want to decompose this according to the shape of the parameter. All right. So this is what we call a weak form of beyond endoscopic decomposition. Okay, so I will. Okay. So given a partition as before, like this, okay, partition of 2n into sum of these positive even integers. So let's define H, just a product of this smaller odd orthogonal group. All right, so therefore the dual group is just product of this smaller symplectic group. And one also has a embedding of dual of H to dual of G, and this embedding is uniquely determined by the partition, okay, up to conjugacy by G hat. Okay, so in Arthur's paper, Problems Beyond Endoscopy, he called this an example of the elliptic beyond endoscopic datum, which is actually nothing other than a L subgroup of G hat. Okay, but here we are considering a very special situation. Okay, and also note that if K is 2, then this is also an example of an elliptic endoscopic datum, okay, of G. But when K is bigger than 2, then it is not. All right, so as I said, H is just a product of odd orthogonal group of smaller size. So in particular, we can apply endoscopic classification to each of the factors of H. So for instance, the square interval parameter is just a product of the square interval parameter with each of these factors. So let us define a certain subset, okay, so phi primitive, okay. In fact, it should be called weakly primitive, but I just call primitive, okay. Phi primitive to consist of those parameters, so such that each of these phi I is simple, okay, respect to the smaller orthogonal group, and phi I and phi j are not equivalent when I yield to j, Okay. Of course, this condition is only relevant if mi, if the size mi is equal to mj. Okay. All right. So the main point is follows. So in this beyond endoscopy project, so of course, say given a parameter, okay, so you would like to, in some sense, detect the functorial origin. So namely that one would like to find a smallest L subgroup or LG, such through which this phi factors. Okay, so let's call this rho. Okay, so here we are doing something much more modest. So namely that here our H is just a product of smaller odd orthogonal group, and here, so therefore we are simply, okay, so let's say phi is a cuspidal parameter, so we are simply looking at the smallest H that is of this shape, namely that is of the product of odd orthogonal group of smaller size, through which this parameter phi factors, okay, and it factors through such a phi prime that is weakly primitive in the previous sense. Okay? Yeah. So now, given such an H, okay, and a test function respect to H, let us define the following. So P again stands for primitive, okay. So define this distribution respect to H by a in some way by a just look at this sum of these stable characters respect to the parameters phi prime that are primitive. Okay, so in other words, here you just sum over those parameters that are in here. Okay. In particular, if H is G itself, then the sum here correspond to those simple parameters, right? So, this is again stable, okay, by construction. So now we can state the theorem. This is nothing other than rewriting the stable multiplicity formula, okay. So let f be a test function on G, okay. So as before, we have this cuspidal component of the stable trace formula on G. So we have a decomposition like this, okay. So the sum over these H, okay, so this special form of the elliptic beyond endoscopic datum, okay, and certain coefficients which could be described explicitly, and also these primitive version of this cuspidal component, okay. And I need a transfer of test function, okay, so from G to H, okay, so which is this transfer. So firstly, the coefficient is just given by this one. Here, S rho is essentially the same as what we have in the usual endoscopic theory. This component group. And the size of this is just this to the k minus 1, exactly the number coming from the stable multiplicity. And then also, as usual, the outer automorphism occurring in here. And I need to describe the transfer. So this transfer is different from the Lang-Lang-Shell set transfer. Okay, so this transfer of test function is from stable orbital integrals of G to stable orbital integrals on H. Okay, so it is nowadays is referred to as the stable transfer. So this transfer is defined purely locally. Okay, and so given the test function f, so we need to specify the stable orbital integral of the transfer, okay? And this is determined by the condition. So using the stable version of the Trace-Paley-Wiener theorem, which is also a consequence of the local language correspondence as established in Arthur's book. So namely that to specify the stable orbital integral of this function that we would like to construct, so it suffices to specify the stable character of this for each bounded local language parameter for H. Okay, and the recipe is that the stable character, when you evaluate this, is equal to stable character of your original test function on G, and respect to the parameter obtained by push forward. Okay, namely that you have the parameter on H, you just push forward to LG. Okay. Yeah. All right, so this is the stable transfer as proposed by Langlands. So it is a very important question to be able to describe this transfer and on the geometric side. So this condition is prescribed purely on the spectral side, right? So and one would like to have say what would be the analog of the Langlands shell set transfer factor in this setting. Okay, so my understanding is that for the Archimedean case, shell set has a work on this, which should describe what is a kernel of this stable transfer on the geometric side. Okay, so but in any case, all we need is for this theorem, all we need is the existence of this transfer. But obviously, one would hope to be able to establish such a decomposition by working with the geometric side of the trace formula. And for this, one definitely would need to know how to describe how to prescribe this stable transfer on the geometric side. Okay, but in any case, let me go on. In the beyond endoscopic proposal of Langlands, he proposed to construct certain limiting form of the stable trace formula. So for each finite dimensional representation of the dual group, so you like to insert the order of poles of the L function into the cuspal component of the stable trace formula, namely like this. Okay, so namely that you want to insert this term into this cuspal component of the stable trace formula. If R is just a trivial representation, this is just what we had before. And in addition, one would like to establish decomposition. Well, firstly, one would like to establish existence of this, and also hope to establish decomposition of this similar to what we have before. Okay, so similar to this type of decomposition. So, and it is hoped that these would provide new tools for establishing the functoriality. All right, okay. So in more details, okay, so one hopes that by varying this R, okay, by varying the dual group representation, we would reflect the functorial origin of the parameter. So as an example, let us consider as before, a cuspal parameter like this. And by result of Professor Dihua Jiang, so if you look at the set of dimension data respect to the fundamental representation of the dual group of G, namely SP2N, okay? So you let R ranges over the fundamental representation of SP2N, then the dimension data, namely you just restrict it to the dual group of H, then this set of data determines a partition, okay? And hence determine your dual group H, okay? Yeah. So here, say the fundamental representation A from 1 to n, so these occurs in the following short exact sequence. So you take the exterior power of the standard representation on the 2n dimensional space. So you take the cup product with respect to a symplectic form. So and then the kernel is this A fundamental representation. So using this sequence, so for example, say for the first fundamental representation is standard, okay, and the second fundamental representation is just a factor of the exterior square. And using this, one can, as in Professor Jiang's paper, so show that, say, the dimension data, okay, so of course it's just obvious, and then for A is odd, then the dimension data are all 0. So now, for cuspal parameters before, therefore, one expects that this equality to be true, okay, so namely that the dimension data, okay, respect to this H, okay, so product of these smaller odd orthogonal groups, okay, respect to the partition, is to be equal to the order of the pole of the L function at S equal to 1 for any finite dimensional representation R of the dual group if the parameter does not factor through any smaller L subgroup. Okay, So in particular, in such a situation, then the set of data, namely the order of poles of these L function respect to the fundamental representation, would determine this H hat. Okay. Yeah. So of course, in the general beyond endoscopic proposal, this is what Langlands hope that if you let R varies over all representation, finite dimensional representation of dual group, it would actually pick up the he called lambda H, okay, in some sense the smallest L subgroup through which your parameter factors. So the problem, of course, is that we don't have analytic continuation of the L function in general. So the definition given previously is only a motivation. And what Langlands proposed is that you try to construct this, okay, mainly using the geometric side of the trace formula, and by using modified form of test functions. Okay, so as before, S is our fixed set of valuation, and so now let's fix a place W now in S, and for an integer, positive integer, and also a finite dimensional representation of the dual group. Let us define an element in the spherical Heck algebra. Okay, and we prescribe this in terms of the Sartaki transform, namely Sartaki transform of this when evaluated as a semi-simple conjugacy class is just a trace of this trace of RC to the n. Okay, in fact, for our purpose, the most important, in some way, the most important case is n equal to 1. Okay, so if actually you can just put n equal to 1 and ignore this n. Okay, yeah. So now for a global test function, okay, so the spherical valuation outside S, let us define the following modified test function. Okay, so again, respect to each place W and in positive integer and R. Okay, so in fact, we modified it only at the place W. Okay, in other words, at a place other than, so at a place V other than W is still the same test function. While at the place W, then this is modified. You just convolve this with this function in the spherical Heck algebra that we have as before. Okay. Yeah. So and then let us form the following Dirichlet series. Okay. So in other words, you use this modified test function and plug into the cuspidal component of the stable trace formula, and then you take these as coefficients, forming this Dirichlet series. Okay, yeah. Okay, for a given f, this converges absolutely for real part of S sufficiently large. And the beyond endoscopic proposal is that, okay, so try to show that this has analytic continuation up to the region, real part of S bigger than 1, and then analyze the residue at S equal to 1. All right. And needless to say, if one thus has the analytic continuation of L function, then the expression is, then it would exactly give us this, okay? Yeah. Yeah. I should also say that if one thus has Ramanujan conjecture, the generalized Ramanujan conjecture, then the terms involving n bigger than 1 will all vanish when you look at the residue at S equal to 1. But perhaps this form is more natural from the perspective of analytic number theory. Okay, so that's why I put it here. Okay, so as I say, so this is still a very difficult problem. So so we are only trying to illustrate the kind of result one would expect by using the known results on the automorphic L functions. Okay, so namely that these L functions respect to the respect to these fundamental representation. The first two fundamental representation, the L function respect to the first two fundamental representation can be expressed in terms of the Rankin-Selberg type L functions on GLN and also the exterior square L function. So, and the analytic behavior of these L functions are all known. So therefore, so even though it's certainly a very difficult problem to try to analyze this directly using the geometric side of the trace formula, but nevertheless, one can we know what the result we would expect. Okay, so so the theorem is follows. So for the first two fundamental representation, then this Dirichlet series that we have described previously. So this has holomorphic continuation to the region real part of S bigger than 1. So the residue at S equal to 1 exists, and also we have the decomposition. So namely that quite similar to what we have before, except that this coefficient might get multiplied by the dimension data. Okay. All right, so in particular, for the first fundamental representation, then the dimension data is just 0. So for the first fundamental representation, this just vanish. Okay. So for the proof, okay, as I said, okay, so input is from the endoscopic classification together with the known results on the analytic property of these L functions, the Rankin-Selberg exterior square and also symmetric square. So these were due to Scheide, Takeda, and also Dustin Belt, who is a former student of Scheide. Okay. So okay, so okay, let me just end with concluding remarks. Okay, so for SO3, of course, it's just a PGL2, and if R is the just the standard representation, then in this case, the vanishing could be compared with the results in the thesis of Ali Altuk, okay, where he, at least when it's just over Q, when the number field is Q, okay, and also when the test function is special type. So, for example, when it's unramified at all the finite place. So in this case, he used directly worked with the geometric side of the trace formula and established the vanishing. Okay. So perhaps the question is, okay, so the next case would be SO5, and which is essentially GSP4. And of course, the vanishing, okay, something that one would like to prove, but perhaps it's much more interesting to ask for the second fundamental representation. Because for the second fundamental representation, then we would capture those forms that are of Yoshida type. Okay, so namely GSP4 coming from GL2 cross GL2. Okay. Yeah. And of course, the forms of Yoshida type had been it could be constructed by theta correspondence or also as a consequence of the endoscopic classification. But perhaps it would be very important, okay, in order to test whether this beyond endoscopy idea to test this idea would be important to try to see whether one could establish this using the geometric side of the stable trace formula. Okay, so yes. Okay. So yes, this is all I would like to say. Okay, thanks very much for your attention. Yes. Can you say again?
In the S05 case, the second dimension.
Yes, yes.
What's the dimension?
Dimension? What was?
I mean, it's the R2. I mean, sometimes SO5.
Oh yeah, here everything is okay. So the dual group is just SP4.
Okay, so it's just
Yes, yeah. Oh, say again. R3, there's a of course everything comes from the known results on the automorphic L function. But for R3, there's an exceptional pair. for SO7. So as a Levy subgroup of F4, you look at this pair, right? So the Lang-Lang-Shahidi L function respect to this pair give you R3. But only for SO7 because you use exceptional group, right? So yeah, so for this for SO7, therefore you would also get the vanishing for R3, but other than this, nobody knows. Maybe as Freydun once tried to using this Kashmuri group, but nobody really knows yet. Okay.